Well, thanks very much, Barbara. What I'd like to do tonight is to really give you a presentation in two very distinct parts. The first half is going to be a quick synopsis of what we know today about the climate system and how it's changing. And I'll go through and emphasize as we go through what risks that presents, particularly for urban areas. The second part is going to be far more exploratory, and that's going to be using our own city and region as an example of what we might be able to do in more creative and visionary ways to meet the challenges that I'll be talking about. And in that second half, I have to foreshadow that I'm stepping out of my particular area of expertise, and if it makes any sense at all, you can thank Barbara for teaching me a bit about planning and thinking about urban areas, and for the bits that don't make sense, you can blame me for that. So let's get stuck right into the science. This is the iconic figure that everyone looks at. This is the surface air temperature record from 1880 to the present, and you can see quite clearly that since the middle of last century, there's been a steep increase in temperature. It's averaging about 0.17 degrees Celsius per decade. That's actually very fast in geological time frame. The important points here were, I think the decade 2000 to 2009 was the warmest decade on record. So unlike what you might hear in the media, there's been no slowing of the warming trend. You can see that quite clearly when you look at the multi-decadal trend. But there's far more to climate change than just surface air temperature. We can see, first of all, that on a much longer time frame, this goes back to the time of the Roman Empire in the year 200 AD, you can see natural variability. And this hump about in here is the medieval warm period. There's the little ice age. The red line is the contemporary post-industrial era warming. So you can see immediately it's different from patterns of natural variability that you see in the past. It's rising at an exceptionally rapid rate when you look at it on this time frame. And also where we are now is clearly above the highest temperatures that we see during the last couple thousand years in terms of natural variability. But we can see other parts of the climate system that are shifting too. This is Arctic sea ice from 1979 to 2007. You can just see the shrinkage of that. There's the data, the red line of the observations of how much sea ice is remaining at the end of summertime. The black line are the model projections. So in this case, the models are actually too conservative. They're under-predicting what's actually happening to the Arctic sea ice. This is a really important one that's often neglected in analyses of climate change. This is the ocean temperature. And again, you see from 1950 when we first had reasonable measurements, you can see, again, the last 50 years, ocean temperature has been rising steadily. Why is this particularly important? Well, those of you who've done first-year physics realize that the heat capacity, thermal capacity of water is much, much greater than that of air. So in fact, somewhere between 80 and 90% of the extra heat that the greenhouse gases are trapping at the Earth's surface actually end up in the ocean. So for a single indicator of what's happening to the Earth's climate, this is actually much better than air temperature. And the trend is absolutely unmistakable. And we can see it in sea level rise too. Again, here are measurements of sea level rise, first with tide gauges, and then later from about early 1990s onwards, we've had satellite measurements which give us much more accurate and precise measurements of what's going on. And you can see again, sea level is rising quite steadily, a bit of variability from year to year, but the long-term multi-decadal trend is clear. Right now it's rising at an average of 3.2 millimeters per year. We make an estimate that by 2100 compared to 1990, sea level will be a half a meter to a meter higher, which has really important implications for a lot of Australia's urban areas because they're located around coastlines. So the question then, of course, is what is causing this? Well, I've certainly hinted that by that long-term record from the Roman Empire showing that this isn't natural variability. But we can go much further than that in attribution because we know a lot about the climate system. This is a cartoon of the greenhouse effect. Many of you probably know this, but for those of you who haven't heard it explained before, this belt of gases in the troposphere, the lowest part of the atmosphere, of which CO2 is the one that's been rising most prominently over the last century or so, these have properties that absorb outgoing heat radiation from the Earth's surface. So basically the sun's the energy source for the Earth, of course. Some of the sun's incoming radiation is actually reflected. A lot of it's absorbed by the Earth's surface. To keep an energy balance, the amount of energy that's absorbed has to be re-emitted in some way, or else the Earth would continually rise in temperature, which it doesn't do. So this is the way the Earth gets rid of that energy and keeps in balance. It emits heat, not light, from its surface. And that heat is of the appropriate wavelength to be absorbed by greenhouse gases. So that's what keeps the planet inhabitable. If we didn't have them, it would be 33 degrees colder. It would be frozen all the time. So it's a good thing we've got them. And of course, the basic physics tells you that if this belt of greenhouse gases increases in concentration, you're going to absorb and retain more heat near the Earth's surface. Nature has done this in the past. It's removed and increased the amount of greenhouse gases, and temperature has responded accordingly. So when humans do it, it's a no-brainer. The climate system will respond as the physics says it will respond, and that is we will increase the surface temperatures I've just shown you. So this is the CO2 record. Now what I've done here is taken an ice core record. This goes back about 420,000 years. It's a long time frame. Just to give you an idea, humans appeared on planet Earth about here. So we've experienced a CO2 that has oscillated between about 180 and 280 parts per million. As a matter of fact, before the Industrial Revolution, it was sitting at about 285 parts per million. The red line is the additional CO2 that's been added since the Industrial Revolution. And you can see that we've doubled the operating range between an ice age and a warm period, which is what these two levels represent. So this is telling us that this is a really, really very big change to an important factor in how the Earth system operates. And given the radiative properties we know of greenhouse gases, this is telling us that this is the likely candidate. And in fact, when you actually do the sums, knowing the actual properties of how much radiation CO2 absorbs, the numbers fit. The amount of warming we're seeing fits the amount of CO2 in the atmosphere. So that quantitative calculation also gives us some confidence that we know that that's the main factor. Now this is an interesting one because what we've done here is we've taken a climate model and run it in hindcasting mode. In other words, instead of trying to predict the future, we've seen how well it can actually predict the past. So we've run it from 1900 to 2000, and we've run it for every continent. This sort of greeny colored wedge here is if you only put in natural variability, change in solar radiation, change in volcano, and so on. The purpley line is if you put in addition to that, you keep those in, but you put in the extra greenhouse gases. So the green line has no extra greenhouse gas. It's only got the 285 parts per million. The purple line has the increasing greenhouse gas concentrations that have actually been observed over the last century. And the black line are the observations. So again, this is a way we actually test the models to see if they can actually simulate what we really observe in the climate system. And here you see they're really good. Continent by continent, they get it right. And when you average it globally, they're really good. So again, this gives us confidence that the additional greenhouse gases are the primary cause for the warming that we're seeing. There's other evidence too. It's things that we call fingerprints. And one of those is that it's a globally synchronous signal. I showed you that just on the last slide. Every continent was rising in temperature. If you go back and look at the medieval warm period, for example, you see that it was mainly a northern hemisphere phenomenon with so-called teleconnections to the south, the more muted response in the southern hemisphere. So when you look at a lot of these patterns of natural variability, what you find is that they are associated with changes in ocean-atmosphere coupling or in ocean circulation or atmospheric circulation. So it's a redistribution of existing amount of heat at the Earth's surface between ocean and atmosphere and between geographical regions of the Earth. But what we're seeing here is additional heat coming into the system due to those extra greenhouse gases. So that gives you a different fingerprint. Another fingerprint is the troposphere is warming, but the stratosphere is cooling. Now that makes sense because the greenhouse gases are actually found primarily in the troposphere, so that's where they are acting. So the additional heat is trapped in the lower troposphere and the surface. But less heat is going out through the stratosphere, and you see that, in fact, with the stratospheric temperatures cooling. So again, this is a so-called fingerprint. If it was the sun that was warming the planet, it would be warming the stratosphere as well. You get warming right through the atmospheric column. So again, this is a so-called fingerprint. Another example, winters are warming more than summers, and nighttime temperatures are rising more than daytime maximums. Again, this is classic behavior of greenhouse gas forcing rather than solar forcing. So there are a number of what we call fingerprints that are all consistent. So the point is there's a large body of theory, of observations, and of calculations that all are internally consistent, that match with the fact that the primary forcing of the increase in heat at the Earth's surface are the additional greenhouse gases. So these two aspects of the science are very well known and are not disputed in the primary scientific literature. If you go through that, you've got to go back several decades to start finding and tracing back when these debates occurred in the credible scientific community. But like in many areas of science, things get settled. We go on generating new questions, new areas of controversy, complexity that we need to work on. And that's what's happening in climate science, just like other areas of science. So to summarize this, these 2 points I think are really clear. Warming of the climate system is unequivocal. That word unequivocal was one that was used by the IPCC in its 2007 report, which is a very carefully worded conservative report. So when they say unequivocal, well, you know what the word means in English. It doesn't leave much room for doubt. And the evidence in the 5 years since the science of the IPCC Fourth Assessment Report has actually strengthened that conclusion. And I've given you some of the evidence. It's not just air temperature. It's right throughout the Earth's system. The second point is I've just noted there is really now a very large body of consistent evidence for the fact that since the middle of last century at least, the primary cause has been the increase in greenhouse gases in the atmosphere. The most important of these is the long-lived greenhouse gas CO2. And I don't have time to get into some of the feedback mechanisms in the Earth system that amplify the initial warming of the CO2, but they're also very important. So this part of the science is very well understood. The debates you hear about it are in the blogs and in the media. They're not in the scientific literature if you go right back to that. So what are some of the risks associated with this? I'll just go through a couple of them, and now I'm talking more directly what it might mean for our urban areas and our surrounding regions. Here's a good example of what it might mean for urban infrastructure. This is a fairly crude, simple inundation map, and the parameters were quite simple. A 1.1 meter sea level rise coupled with a high tide. And I emphasize here we did not apply a storm surge to this. So this is without a storm surge, which would complicate this and intensify it. So this is Brisbane Airport. Most of you probably have flown in at one time or another. There's the landing strip as it is today from a satellite image, and that's with the 1.1 meter sea level rise and the high tide. Now, some commentators say that we're headed for more than a 1 meter sea level rise this century by 2100. There's a lot of debate in the community. I think the best range is 0.5 meter to 1 meter. So this is definitely a plausible scenario that engineers need to worry about. When you put a storm surge on that, it gets even worse. When I've presented this map at meetings where there have been investors in the room, they've come up to me to talk to me afterwards about this because, for example, if they're investing your pension funds in this, it's probably an important thing for them and for you. So these pieces of information are important for people who are making investments now for infrastructure that's going to be around 50 to 100 years. This is one of the reasons why there's some uncertainty. We've got a fairly big spread of data of what's happening to this piece of real estate. I'll return to the Greenland ice sheet in a moment. But this is one of the main reasons why we think sea level rise may be more than what the IPCC estimated in 2007. More recent measurements here by satellite altimetry and also by so-called GRACE measurements, which measure the Earth's gravimetric field to very fine detail, are showing that we know the direction of what's happening. That ice sheet is losing mass. There's some debate about how fast it's losing mass. But it's a big ticket item. It contains the equivalent of about 7 meters of sea level rise. So if it starts losing ice at a faster rate, we're going to go up in our estimates of sea level rise. Water supplies, again, a big issue. Here we have a sort of a tale of two cities that are going in different directions, which is interesting. This is Perth, this is Melbourne. So I'll start with Perth, and you see from 1996 down to 2008, a steady drop through the year of how much water was coming into to the Melbourne dams. And at the height of the drought, they were down to a little bit less than a third of their total capacity, which is a very scary situation for them. Interestingly, if you put back up to 2010, they're back up toward the top again. Very heavy rainfalls over the past 12 months or so. If you go to Perth, you get a different story. You get a switch about the mid-1970s, sort of a step change drop in rainfall. It goes along for a while, and it's dropped off even more. And in fact, they're still in the grip of a very severe drought. They did not get the rainfall that the eastern states in Australia got. So here's a case of where we think we have good evidence that this sort of drop does have a climate change signal into it. It's related to the so-called southern annular mode and shifts of that southward. This one we're not so sure, because there are more complicated patterns of natural variability, and it's hard to tease out exactly what climate change is doing there. The long-term projections by the majority of models, but not all of them, is for drying conditions here. So we still have a lot of uncertainty about what's going to happen to rainfall in eastern Australia. So here's an example of where there is still debate, legitimate debate in the credentialed scientific community. We don't understand what's happening to rainfall in the east. And that's summarized in this graph. If you look at the pattern since 1970, and if you take this out to 2010, despite the last year's rainfall, it's still an overall drying trend. Here we can attribute it with some confidence. We see climate change signal. Here we cannot. Possibly in the far southeast, but we're still not sure there. Really don't have a good idea up in Queensland. Extremes are something people are talking about after the cyclone and the floods in Queensland and the southern states. And here's the basic principle by which climate change affects it. Assuming no change in the shape of the variability curve, if you shift the mean, say by 1 or 2 degrees Celsius, you get surprisingly large changes in extreme events. You can see this from the shape of the curve, is that what you might have defined as an extreme event with the earlier climate, say where this broken line is, when you shift the mean a bit, you get a much higher incidence, much higher probability of incidence of extreme events when you keep the same definition of extreme event. But interestingly, you have a new tail. So you start getting extremes beyond what you experienced before. We actually have a good example of that, and that's Melbourne in February in 2009. When they broke the record, not by 1/10 of a degree or 2, but nearly 3 degrees. They got up to 46.3 or 46.4. So you're going to see more record hot weather. And in fact, we do already see that. I'll show you that in a moment. Well, here it is. Here's the record number of hot days by decade. And in a stationary climate, you see about the same number decade by decade. But you see a trend there. And you see the trend really going up this last decade. So this is telling us that the probability of getting very high extreme temperatures and high bushfire weather, severe bushfire weather, is going up. Again, here's the example of Melbourne. Obviously, health impacts, direct health impacts. These are the excess deaths compared to normal deaths during this period, peaking when temperature, of course, was very high up in the, well, here we can see the temperature up in the mid-40s, which is unheard of for Melbourne. And notice that it kept up at these very high temperatures for a period, and it was at the end of this period, this cumulative impact on health that gave you the highest death rates. Obviously, it affects urban infrastructure as well. That's the classic picture of transport. It also affected electricity supplies. So we have to plan for a world that's going to look increasingly like this. Our infrastructure is planned for this at the present. Bushfires. These are some simulations of what might happen to the bushfire regime of the Australian Capital Territory and the surrounding region. This is what we see today. The color coding is on the return interval. In other words, the number of years between a severe fire. So you see that for the forested regions to the west and northwest of Canberra, that's when you have the shortest return interval. Obviously, in agricultural land, bushfires are much less frequent. But as you go toward a mid-range IPP climate scenario, not the most severe one, you see a quite significant increase in the frequency of severe bushfires. In other words, by the time you get to 2100, the forests are going to burn just about as fast as they regrow from the previous fire, if they're still around. Rainfall extremes, highly contentious subject at the moment. Again, a good example of climate science that is not, that there's not a consensus about. So here's some of the data we do have. Looking at it globally, what we see is that there is an increase in water vapor in the atmosphere. Okay? Now that makes sense because the basic physics tells you if you warm the atmosphere, it can actually hold more water. So the physical theory says you should get an increase in evaporation globally, and that should be measurable as increased water vapor in the atmosphere, and indeed you see it. Again, it's a noisy trend, about 1.2% per decade. Now the interesting thing is, what does this mean to precipitation? It could come down simply as more drizzle evened out over the year, or it could come down as more extreme events. Well, what's happening? Well, the data is just perhaps starting to see a trend toward more heavy precipitation events. This shows you the amount or the fraction of precipitation, percentage of precipitation that comes in the top 5 percentile. In other words, it's above the 95 percentile, the most intense events. So you see that you're getting an upward drift. More of the rainfall is coming in those events. And here you see an example of the United States. This is the area of the United States which is subject to very heavy rainfall events. And you see a lot of noise in this through most of the 20th century, and then the last 2 decades, you clearly see a trend coming there. Now, what about Australia? We don't have enough data to statistically pull out a trend like that. The physics is obviously the same around the planet. So we say that there is a risk that Australia's rainfall events will become more intense, even though we can't prove it statistically yet. So you will see scientists say we do not have any evidence that the Queensland, that the rainfall events that triggered the Queensland floods were intensified by climate change, and that's true. Statistically, we can't see it. But we see almost record high sea surface temperatures off the Queensland coast. We see almost record intense La Nina. And the question is there a link between those two? Again, the science isn't secure enough to say that definitely, but the basic physics is warning us that we should expect more intense rainfall events as we go forward. So summary, what are the sort of things we're going to face in our cities and regions? Increased frequency of heat waves, we can say that with some confidence. More intense storms and extreme weather events. Well, I've just talked about that. The basic physics says you better be aware of those. Droughts last longer and are more extreme. Well, they're going to be more extreme even if you have the same rainfall you had before, simply because the temperatures are higher. So plants and animals going through them have the same rainfall deficit if there's no change in rainfall, but they're subjected to higher temperatures, so that increases the stress. Increased incidence of heavy rain events, probably. Increase in dust storms, bushfires, heat stress, yes, that's, we can say that with higher probability. So those are the sort of things we need to be prepared for in terms of adapting our cities and regions. All right, what do we do about it? Well, this is something that I talked about today in the update report that was released. The name of that report was the critical decade, and this diagram shows why it's so. The top panel are the emission trajectories. This is what's already occurred. You see, we're about here, this 2010, about where those two lines bifurcate. So basically, we've got a choice now to do nothing, and that red line is what the projected emissions would be if we do nothing, out to about 2100. Actually, 2100 would be above that. This is with very effective climate mitigation. In other words, we really get our act together. Now, why do we portray the bifurcation here? If you actually do the sums, and I'll show you that on the next graph, this is about the last point you can bifurcate and have any chance of getting these sort of emission trajectories. Okay? So that's why we say it's a critical decade. The decisions on investment, turning the curve around this decade is essential. Now, this is the corresponding temperature correlated with these two emission reductions. So if we follow this vigorous emission reduction, basically decarbonize by the second half of this century, that's what this is saying. This blue wedge is what temperature does. Notice that it stabilizes just at or below the 2 degrees C guardrail that most countries have signed up to. So this gives us a good probability that we won't go above 2 degrees. We'll have a world we can probably adapt to. If we don't know anything about climate change, this is where temperature is projected to go. Well, you can see what those temperature ranges are. They're pretty high compared to what we've had pre-industrially. So I think the point is this is the critical decade for making the choices that are going to put us on this trajectory or that trajectory. Now, looking at this in more detail, these are three possibilities. If I just go back, if you look at this line, there are several possibilities of doing this. We can wait even a little more and then drop it a little more rapidly. So if we split this out, this part of the curve here, this is what it looks like. So what we're doing is saying, sometime this decade, we're going to need to peak emissions and get them down. Now, one of the surprising things is how sensitive these curves are to the peaking year. The difference, say, between 2015 and 2020 is a difference between a 9% reduction per year in emissions later on and a 5% reduction. This one is almost completely impossible. You simply can't roll out infrastructure that fast. This one, well, it's a big challenge. 2011, of course, we can't meet that because we're halfway through 2011. Emissions are still going up. That would have allowed us a 3.7% reduction after that. So this is another reason why this is the critical decade. To meet that 2-degree guardrail, we've got to get emissions turning down very fast. So that's the challenge we have. We've got a double challenge to our cities and our regions. One is we're going to have to cope with even more climate change than we experience today. That's already in the pipeline. And two, to keep that climate change manageable, we've actually got to get emissions down. Now, I read somewhere that 3/4 of the world's emissions come from urban areas now. And it's often said that it's in urban areas that climate change is going to be won or lost. So now let's switch. I'll switch to the second half of my talk and talk a little bit about what we might want to do. So this is my transition slide. You might say this is a really strange slide to have as transition. Well, let me give you the context. This is a fjord, and it's in southern Greenland. So this is where this ice sheet is starting to break up. As a matter of fact, About 30 years ago, there used to be a tongue of ice out under this fjord. It's now retracted back up the slope somewhat. The gentleman here with his glass of whiskey is the King of Sweden. And he is running what he calls a royal colloquium. Every 2 years, he's interested in science. He gets scientists together, talk about important issues. So this was the second of 2 that I was invited to, and it was on the big changes that are happening to the planet. And we went to Greenland to look firsthand at what was happening. Now, the interesting thing is the ice in his glass of whiskey came right from the bottom of that ice sheet, went right up to the face of it, chiseled it out of the bottom. This came from the last ice age, probably about 80 or 90,000 years ago. So this is old ice, but it's moving into the sea very, very quickly. Now, why did I show this picture? Well, I was up in Stockholm last week, and I had the opportunity to meet the king again and have a chat with him in an official function. And I said, well, how are the royal colloquiums going? He said, great. The last one was on urbanization, and we had it 2 weeks ago. We're moving on to solutions. So I think just this progression of his royal colloquia is exactly the issue that's happening now. We're understanding the problem, and now we're saying, hey, look, we've really got to focus attention on solutions. Okay, so let's dig into this. Australian cities, there are a few of them there. You might recognize them. And the issue is here, what are the challenges? Obviously, I've talked about climate change. But one of the points I want to make straight away is we cannot look at climate change in isolation. This is a big one, peak oil. And I think it could bite even sooner than climate change. Demographic change. This is happening around the world, particularly in Western countries. And there, I didn't put population only. I put demographic change. Age structure of population is changing. There's internal migration within countries. And in Australia's case, there's immigration coming into, or migration coming into Australia. All of these changes are occurring, and we've got to learn to deal with them in cities. Let me just have show you a couple of slides of peak oil, because I've talked a lot about climate change. This is what the experts say. This was an assessment a couple of years ago by the UK, looking at all sorts of groups or people like Shell Oil and so on, who are experts in the oil business. This is their trajectory of what production is going to be like. So here we are in 2010 when these future trajectories play out. They're all flatlining. This one's a bit optimistic, but all the rest of them are flatlining. Bear in mind that with China and India developing rapidly, the demand curve is going up sharply. So the question I ask here is peak oil. Strictly speaking, it's a production question. So peak oil could happen anywhere along here, wherever production peaks. But the real issue isn't that. It's a supply-demand issue, because we have a global demand system for oil. It's a global commodity. So that's the real issue. And I would argue we're already hitting that. Let me just show you what's happening to oil prices. Here's what's happening. We have a big spike around 2008, all right? And that's probably due to rapidly increasing demand. And this curve is probably sensitive to increases in demand from China and so on. What happens? We trigger a recession. Demand drops, prices drop, everyone thinks it's okay. We start coming out of recession, and look what happens to price. So the question is, this is only a short record, but are we going into a pattern of instability in oil prices? We trigger recessions, come out, higher oil prices, trigger recessions, with perhaps an underlying upward trend in that curve. All right, so that's one thing we've got to face in cities, particularly in Australian cities and American cities and so on, who are heavily motor car dependent. We are very much dependent on what happens to this price. Now, it isn't only transport, of course. That's the one we think of immediately because we think of putting petrol in the car. But now look at the shape of this curve, because I want to show you something that's quite striking. Watch how it drops, a few jagged bits there, and then comes up. There's food price. Okay? Look at what's happening. There's 2008. There's the spike, comes up, a few jagged bits, and now it's actually even higher now in 2011. There is a very close correspondence between what's happening to oil prices and what's happening to food prices. And this leads to instabilities in places like the Middle East, where poorer countries feel this really, really hard. Why is this so? Well, right throughout the food production system, oil as an energy source is important. It's important for production, it's important for transport, it's important for processing, it's important for retail. So again, I'm arguing here that this is a really important global driver, and it may bite quicker than climate change bites. So we have to look at both of these. All right, here's what I think are some basic principles when we start talking about how we deal with this, particularly with regard to urban areas. One is don't separate mitigation and adaptation. You'll get perverse outcomes. They're not separate activities. They need to be integrated. A classic, well-known example that we already take into account An adaptation mechanism for dwindling water supplies is to put a desal plant in if you sit on the coast. Obviously, it takes a lot of energy. If you use fossil fuels to generate that, you're increasing the problem. You get a nasty feedback loop. Now, we actually understand that one really well. And for example, a capital wind farm near Canberra was originally set up to offset the desal plant in Sydney. And I mentioned that climate change and peak oil need to be considered together. Now, the other thing is we really need to put all of these in the context of what we actually are dealing with already in cities: health, affordable housing, livability, economic vitality, education services. These are all things that drive how we manage, how we plan, how we develop cities. These two things here, these big global drivers, are additional stresses that, again, intersect with all of these. It makes it harder, but on the other hand, if you look for the right synergies, you can get win-win situations. I'll try to talk about that in a moment. And last, we've got to connect urban with regions. There's some wonderful examples in Europe, for example, of Switzerland, of looking at their cities as a network of cities embedded in a region, and looking at the network and not the cities in isolation. So these are, I think, what are some important principles that we need to look at as we go forward. Oh, you can't see that very well in the red, but I just wanted to go back now, talk one slide about adaptation. And these are some of the things you can do to these 5 things in terms of improved building infrastructure, emergency management. I'll just talk about one of them, and that's the heat waves in terms of health. What do you need to do? Well, you need to improve buildings so that they can withstand or they don't heat up as much when you get a very high temperature event. Emergency management's important, but social networks are really important so that people support each other. And it's people who are more vulnerable, young or old, and who are isolated that really are the victims. So again, you see that something that seems fairly simple, you get a high temperature event, people die of heat waves. When you look at adaptation, it becomes more complex. But these are the sort of things we need to do. Well, I won't go on in the interest of time from all of those, but you can tease those out in other bits of literature. Well, let's go to mitigation and talk about that, because as I said before, this is a real challenge. If we don't get on top of this, forget about adaptation, because we'll have climate change we can't deal with. So we've got to get on top of this. Well, what are the big 3 in most parts of the world? Well, obviously, a big one is energy systems. Another one is transport, and another one is built infrastructure. Canberra, absolutely, these are very important. Energy systems, of course, right now we're on the grid, so we don't generate any in the ACT. But these 2 are big ticket items in terms of our emissions. But the interesting thing is this slide tries to indicate there are a lot of technologies already out there that can solve this problem. We know how to generate energy with no emissions, and the costs of this are rapidly coming down. We know how to transport people in comfort and with considerable speed. And if you're using renewable energy to generate this, this is a very low carbon way of moving people around. So we know how to do this. Countries do this already. And of course, built infrastructure, there's a lot already done. And of course, if you came to the first CURF inaugural seminar, you would have heard from Romilly Madhu that Canberra actually leads Australia in the number of 5 and 6 Green Star buildings. So we actually have some runs on the board here in Canberra of being able to build infrastructure that's far more efficient than what we've had in the past. So, from business as usual to transformation, this slide really I should have put CURF on it, because this is really what CURF aims to do. And that's to promote this idea of co-production of knowledge. And that's to get away from this notion that academics sit in universities, do research, and then transfer it or transmit it to users, which is the way I was brought up with earlier in my career. But the notion now is that the researchers actually work together with government, private sector, communities from the beginning of the research. So in other words, the questions are developed in collaboration with the people who are actually going to use the outcomes of the research, and they're involved all the way through. So there is no problem with communicating the outcomes of the research and so on. Okay, well, here's some examples of a couple of these types of things that we might apply to Canberra, and these are only ideas I'm putting up for discussion. This is, I think, a provocative one, but we should think about it. What about a scenario study? Now, when you look at global scenario studies like the Millennium Ecosystem Assessment, one nice way of doing it is to look at 2 major axes that define what your future might look like. What I've taken here for the sake of argument is a global one, and that's that bifurcation I showed you. Are we going to a 2-degree world, or are we going to a 4+ degree world? And then you have a local regional one. Are we going to be proactive? Are we going to anticipate, adapt to, mitigate? Are we going to be on the front foot? Or are we simply going to be in reactive mode? Something clobbers us and we try to patch up afterwards. Those are 2 very different strategies. And you can develop 4 different scenarios. And here I just put little tags on them. If you're proactive and we have a 2-degree world, we're probably a world leader in how you do that. If we're proactive and you get the 4+C world, we're going to get clobbered like everybody else. So we may be battered but not broken because we're proactive. We may survive. Other cities may not be so lucky. If we don't do anything but just sit back and let things happen to us, and we get a 2-degree world on the backs of other people's actions, we'd be a free rider. And that's the complaint other countries are starting to make about Australia right now. If we had a 4+C world and we don't do anything to try to adapt to it, this is a decline and collapse scenario. So these are the sort of futures that we could see toward the second half of this century. This is a way of organizing our thinking to deal with these challenges. So what does the scenario approach do? Well, it engages governments, business, planners, communities in a common endeavor to tease out where we possibly could go. It builds consensus toward a common future if it's done well. A good example of that was South Africa. Back when it became clear that apartheid could not continue, South Africa went through a scenario exercise. All but one of the scenarios was so horrible in terms of violence that only one stood out as feasible, and that was the one they chose. So it can have a huge impact. It encourages long-term thinking beyond incrementalism and so on, examining goals and values. And it gets to this idea of stretch goals and backcasting. What are some really big goals we can meet, we can have that look impossible, but then backcasting step by step by step, how do we get there? So a lot of interesting things that come out of scenarios. It's now a widely used approach internationally to deal with these possible futures. So what do? Well, we develop basically 3 types of things. The drivers, I've already talked about. Storylines, that's building a convincing story. And then outcomes for things like health and well-being and so on. Okay, just to conclude, what's something else we could do? And here's something I just put up, and I acknowledge that I've got some very nice maps from ACTPLA. So Neil, we do look at these reports, and you provide some very useful information. Here's something that Canberra can do. A transport and urban forum. How do we go toward a real low emissions future, but then look at all the other values that we want to have in a city? Well, first of all, we start thinking nodally and regionally. Canberra actually has a big advantage. It's built around nodes already. Even though it's somewhat sprawling, it's got advantages over other cities. So you start thinking about connecting the nodes. And of course, I don't want to think about Queanbeyan, or forget about Queanbeyan rather. This node here I put in was the airport, if we want to think about that as a transport node. Well, here's an example of how you could do a transformative project big enough to probably really make a difference, small enough that we might actually do it. And the idea is to use the inner north as sort of a test bed for how you start transforming Canberra. The idea here is put a couple of things together. This is the first stage of a light rail that simply goes from Epic down through Northbourne, Civic, out Constitution Avenue to the airport. This is where we already see from the ACTPLA maps we've already got density, and we're getting more density there, and we'll get a positive feedback. But then we also want to trigger some new developments in residential. And here again, I'm pitching an idea from Romilly Madu, who they're thinking about going from Green Star buildings to Green Star communities. And she had some wonderful ideas about that. How about using this as an experimental area? We try some new Green Star communities along the Northbourne Avenue axis and maybe along Constitution Avenue. And Civic, well, Civic needs some work. If you've been into Garima Place and around there, you know that there's some issues. Well, we have one model here in terms of City Plaza apartments of how we can get mixed residential, commercial, very attractive right in the heart of the city. Why don't we do more of this down City Walk? It could be a wonderful part of Canberra, both for visitors and residents. And of course, then we've got the airport hub. Now, I'm not talking about regional too much today, but here's a good example of how, if we're thinking regionally, you might want to put in a new modern rail line to Cooma and build a link there. And again, it would fit in nicely, maybe making the airport as the hub there. Anyway, these are simply some ideas, the way we need to start thinking about something that is transformative, but yet is manageable enough we might actually be able to do it. And in terms of just the transport itself, I've talked about light rail, but in fact what we want is a really integrated system with bus, electric vehicles, cycleways, and walking corridors all fitting into a system that works together. Now, looking at all of Canberra may be too big to bite off, but if we do the inner north, we may have a chance of doing it. Last one here, what other advantages does this give us? Going to a more compact city means we can do more of this. Ecosystem restoration. We have a superb example out at Guyaroo Mulligan's Flat, where we're rehabilitating, restoring a woodland, and eventually putting in the small marsupials that used to be in there. Can we do more of this? Maybe a riparian zone along Lower Molonglo River, and maybe others. And so here you get a synergy. By making a more compact city, you can actually enhance Canberra's value as a bush capital through very innovative ecosystem restoration. Concluding remarks, the 4 things I'd like you to take away. Global change really means business as usual cannot continue. We really can't survive the rest of the 21st century simply doing what we've done in the 20th century. Taking a systems approach allows us to look for synergies, trade-offs, and feedbacks. I just hinted at synergy there at a more compact city and yet an enhanced bush capital at the same time. Think regionally. I haven't talked much about this, but we have to do this. A well-connected regional system of nodes is the way a lot of people in Europe are thinking about it. Research and education, it has to be part of all this process, but it has to be much more interdisciplinary, much more connected to the community. Think CURF. So let me stop there. I want to quote from a Nobel laureate author, which I think is really good. When you think all of this is too hard, she made a wonderful quote, Nadine Gordimer from South Africa, which faced big challenges. Never be afraid to go too far. The truth lies beyond. So with that, I'll close, Barbara, and have some discussion.